Hi, in this tutorial, I will show you how to solve Eulerian residence time using the advection diffusion reaction equation in FEniCS. So this Eulerian measure for residence time calculation was proposed by my friend and colleague Mahdi Esmaily in this nice paper. And later in our work, we compared it with several other types of residence time calculation, both Eulerian approaches and Lagrangian approaches for calculating residence time at flow stagnation. So in this talk, we'll focus on the Eulerian residence time, the one first proposed in this nice paper here. So this is the equation we're interested in solving. It's essentially the same advection diffusion equation I solved in the earlier tutorial, but with the source term added. And that source term is equal to 1, and it represents time that's being integrated. Okay, so this C that you're solving here, you can think of it as your Eulerian residence time. And the source term, you typically can set it either to 1 everywhere, or you can set it to 1 just in the region of interest. And as for boundary conditions, you set 0 at the inlet, 0 Dirichlet boundary condition at the inlet, and at the wall, you would not specify any boundary condition. So unlike the previous case where we had the flux boundary condition at the wall, which typically happens in biochemical transport, in this case, we don't have any boundary condition. So 0 flux, 0 Newman at the wall. And that makes this equation much easier to solve compared to the previous equation I talked about, because in this case, in the residence time case, we don't have boundary layers. We don't have those thin boundary layers. So that's much easier to solve. Okay, so I will go over this code to how to solve this equation. The code is pretty similar to the last code that I talked about for solving 3D mass transport, with just this source term added and slightly different boundary conditions. Okay, but I will go over it one more time again. So the top of the code, we say if we want to use stabilization. Here we're setting all the parameters. We can either read our files in XML format or in the more efficient for parallel processing H5 format. So here I'm reading all the H5 files that I created in an earlier tutorial, the boundary condition tags, the mesh, and the velocity data. And I'm defining how I want to output my file. I'm telling the code that my velocities, I have 50 velocities. These are the velocities that are embedded in my velocity H5 file. I'm telling it every 5 time steps to print intermediate information. I'm telling it to save the solution every 200 time step, and my basis order is set to 1. And here's the diffusion coefficient that I set. And in this case, unlike the mass transport with flux boundary condition at the wall, where it's essentially a near wall transport problem, in that case, as I mentioned in the earlier tutorial, the value of the diffusion coefficient is very important because it will scale all your solution, and quantitatively it will completely change your solution. But in this case, it's less sensitive to that because you don't have the thin band layer, and also a problem is advection dominated. Okay, so how long particles spend, really, if you think about residence time in terms of particle perspective, how long they spend inside the domain is mainly an advection problem rather than diffusion, because of how advection dominates diffusion. So in this case, it's less crucial if we set this the more accurate, very small value. Okay, and the flux, I'm not using the flux boundary condition in this case. Here I'm running the code for 5 cardiac cycles. Again, you need to run this residence time code for several cardiac cycles, typically more than that, for it to reach quasi-steady state. So I think in our paper, we ran it for 10 cardiac cycles. So this is the total number of time steps. This is how your time step is calculated. And then T steps per file tells the code how many time steps we have between 2 velocity files, how many transport time steps we have between 2 velocity files. Okay, and then the rest is just setting up the finite element problem. So you don't really need to change much here. This is the part that you need to perhaps change, and that's the inlet boundary condition. So you need to make sure this tag 1 corresponds to your inlet, where you're setting 0 Dirichlet boundary condition. So that's our Dirichlet boundary condition. And this is our weak form, which is same as the mass transport case, with this term added here. So we have this 1, the source term added here. Okay, and we have also our stabilization. Okay, Then the code moves on to the main time loop, which here is the velocity files. It interpolates between the two velocity files depending on what time step it's at, and runs the code and prints intermediate information. Okay, so now let's take a look at the results we get in this case. This is the residence time results we got. So at the wall, you can see it's pretty similar to the concentration patterns we got in the mass transfer problem. And we talk about that in detail in this paper. Essentially, what happens again is that the Walsh-Schultz's LCS again dictate where you get high Eulerian resistance time. As you can see, for example, in this panel, the blue line is attracting Walsh-Schultz's LCS, and you can see it leads to high Eulerian residence time at the wall. So the same thing happens here. But in this case, the residence time values away from the wall could also be of interest, which you can visualize using different approaches. For example, I can do a volumetric visualization here. And I can also take a slice and visualize my residence time data. Okay, so in this paper, we talk about in detail about conceptually what the Eulerian residence time means, how it differs from other forms of quantifying residence time, like particle residence time, which is perhaps a little bit more common in the field, and that's what we've used in our earlier work too. So I encourage you to read this paper to learn more about conceptually the concepts behind residence time and how the different measures compare. And specifically, the way I like to interpret residence time models is that by thinking in terms of heat transfer, so making an analogy with heat transfer, and that way I can, so this source term for residence time represents a heat source, for example, and you can provide some nice interpretations of these results and compare different approaches, which we talk about in our paper here. Okay, thank you.